Hello, everybody. First, I would like to take this opportunity to thank all the jury members for being here and for taking the time to read my thesis and provide me with very valuable feedback. So I will present my thesis, which is entitled Application Level Virtual Memory for Object-Oriented Systems. So this is the outline of the presentation. I will start with the context, the problem, introduction. Then I will show you my proposal, what I did to validate, then some of the related work, some details about the implementation, and finally the conclusion and future work. So let's get started with the context, problem, and introduction. So the context of my PhD involved the improvement of the memory used by applications. So the idea to reduce the amount of memory that applications use. And why this? Well, first, this is very interesting for robots or any kind of limited hardware where they have a limited amount of memory. And even besides robots, it's also interesting for embedded devices or even a little bit bigger hardware like a cell phone or a smart cell phone or even tablets where we do not have as much memory as we have in normal computers. But that being said, this is also interesting for desktop applications because why would applications use more memory than they actually need? And if we follow this and we think about servers, this is also very interesting because, for example, if application uses less memory, some servers may be able to run more applications in the same amount of memory. So that has a direct economic impact in this case. So what I want to say is that I think that for several points of view, improving the memory used by application is interesting. So the conclusion I get from the very beginning that we need to optimize the memory management for the application. Now, the technical context of my PhD involves dynamic object-oriented languages. So I think it's not necessary to justify nowadays why, but I think why object-oriented, because besides being the most modern and widespread paradigm, what is very important is that usually the language takes care of managing the memory. So usually by a garbage collector. So that means that from the language side, from the language point of view, there could be something that we can improve. This is in contrast, for example, with C, where the developer needs to manually allocate and deallocate memory. So there is little we can do there. And why dynamic? Because I think they are powerful. And year after year, we are seeing that dynamic languages has more and more impact. So the question that I got at the beginning of my PhD is, if we merge this context about improving memory and the dynamic object-oriented, is the garbage collector actually enough for the type of optimization we are searching for? Are we allowed to run object-oriented systems in robots? So to answer that, I took the scientific process. So we measure first. So what I asked is, okay, do applications really use more memory than they actually need? Or in other words, which is the percentage of used and unused objects of certain applications? So what I did is an experiment where I took different applications. These are real-world applications. Each of them has different key characteristics. For example, the first one is the website of the DBEX project, so it's a website. The second one is Moose, which is a tool for visualizing and analyzing software, which the key characteristic is that it's really, really large. It has a lot of packages, classes, and methods. Then we took a mobile app, which is the key aspect, and it is a tool to teach math and geometry to students. And finally, we analyzed Faro, which is the programming language where I implement my proposal that we will see later, because it is interesting to see the environment itself, how good or bad it is regarding the memory usage. So the result I get is the following. First, let's concentrate on the left side. So the red parts represent the percentage of unused objects during the execution and the run of these applications. And the blue represent the percentage of used objects. Now, different objects use represent different amount of memory. So the other question is, okay, these unused objects, how much memory represent? So as we can see also, most of the memory is represented by unused memory. So the conclusion that I got from this at the beginning was that 80% of the objects were unused in these experiments. And if I evaluate that in memory point of view instead of objects, the 70% of the memory was occupied by unused objects. So right ahead from the beginning of my PhD, the results were promising. So that's why I continue. Now, the thing is that we have unused objects that has not been used for a while, but they are still referenced from other objects in the systems. So the garbage collector cannot collect them because the GC always collects objects that nobody else referred to. But since these objects are used but yet referenced, they cannot be collected. And so they waste primary memory, and therefore applications use more memory than they actually need, and that's why it's difficult to run object-oriented languages in robots, and etc., etc. So the conclusion was that no, the GC is actually not enough for this case. The first thing that came to my mind is operation system virtual memory to solve this, because that's what the operation system virtual memory does. It swaps out pages from primary memory to secondary memory and vice versa. But the thing is that the operation system virtual memory only knows about pages. The swapping unit is a page. It's not related at all with objects, which is what we have at the language level. So, it doesn't know the application domain, the operation system. And finally, the developers do not have an easy way to influence the swapping. So it cannot influence or adapt to a custom application. So my thesis statement is that a virtual memory for dynamic object-oriented language should be application aware. That means that developers should be able to influence or adapt the swapping, and efficient. So we should be able to minimize the memory used by applications and minimize the overhead that this system could bring. Okay, so now I will show you my proposal. So what I propose is called Marea. That's the name I put, and it's a model for an efficient application level virtual memory, which is designed for dynamic object-oriented languages. And the key point, the most important thing is that it is based on the swapping of object graphs between secondary and primary memory. So instead of swapping pages, like the operation system, we swap objects, and in fact object graph. This is for efficiency reasons, as we will see later. So if we take a look at the overview of Marea, the idea is the following. We have the RAM memory, which is the primary memory. And we have the secondary memory, which could be actually a file in the local file system. It could be a database, which could be remote or local. It could be the cloud. I mean, it could be some other machine running somewhere. What is important on the secondary memory is almost everything where we can store something that is not primary memory. And the idea is to swap out unused object graph from secondary memory from primary memory to secondary memory. And then if these graphs happen to be needed later on, we have to automatically swap them in from secondary memory to primary memory. So let's take a deeper look to how the swapping works. So in the context of object-oriented system, the memory is seen as a big object graph, where the cycles are objects and the references between objects are the arrows. Okay, so let's say that we want to swap this graph. Let's say that we want to swap this graph to secondary memory because it's in use. So the first thing to notice that what we are actually swapping is a subgraph of the whole memory, of the whole memory graph. The second thing is that the way that the user or the system itself provides an object graph is by providing the root. So in this case, the user or Marea itself provides A, which is the root object, and then we traverse its subgraph, and that's what we swap. So now let's say that we want to swap. So what we do is we serialize the object graph. We get a binary representation, a chunk of byte of the serialized graph, and we store it in a secondary memory. Okay? And then what we need to do is to create a very special object, which is a proxy, which you can see it's much smaller than the original objects in size. And this proxy is a special object that intercepts all messages. So if someone needs that proxy, the proxy will intercept that and will trigger the swap in. Okay? So now when the garbage collector runs, the whole graph can be released from primary memory. That is what we want. And if we now compare, if we now compare the memory occupied by this object graph and we compare it with the original, you see that difference. And that difference is exactly what Marea releases. That is how Marea works. This is the key point. So the difference between after and before the swapping is the gain in memory of Marea. Now, if let's say that the proxy intercepts a message and triggers the swapping, what we will do is we will materialize the object graph and bring it from secondary memory to primary memory, and we get back the original graph. Now let's say that we continue with the same cycle, but we add one little guy here, object D. Okay? So now if we follow the normal procedures, okay, we want to swap the same graph, we swap it, okay, no problem, so far so good, we create a proxy for A, like we did in the previous case. But now when the garbage collector runs, this object C and E will still be in memory. Why? Because they're still referencing from outside the graph. So they cannot be collected. Okay, let's say that first we don't want that because we want to swap the whole graph because the whole graph is unused. But anyway, let's say that, okay, we live with that. But the thing is that if now PA receives a message and we trigger the swap in, what happens when I serialize the object graph, C and E were present in the graph. So if I now just do the normal procedure like we did before, we will get this. And of course this is not correct. Okay? So this is something that we need to solve. So regarding that aspect, it's what we call correctness. So that means that when we swap in a swapped out graph, we should have exactly the same object graph that we have before the swapping. So that's one of our objectives, to be correct. Then we want to, of course, maximize the memory that we can release. And finally, we would like to have as less overhead as possible. So that's our objectives. So I can identify 4 subsystems for Marea. The first one is the object graph swapper. I call it it's the part of the system that takes care of the algorithm to swap out and swap in. We have a proxy toolbox, which is a library that provides proxies that are able to intercept the messages and then trigger the swap in. We have an object graph storage, which takes care of storing and reading object graph from primary memory. And finally, we have the object graph serializer, which takes care to serialize and materialize object graphs. Now, we come back once again to our example, and what I propose to solve the problem of the previous example that was incorrect is to, after we have swapped out, or while swapping out, we identify what I call facade objects. So facade objects are those objects that are directly referencing from outside the graph. In this case, C and A. So I propose to identify them. And why? Because if we then create proxies for them, and only for them, for the facade objects, and then we run the garbage collector, first of all, the whole graph was released. And this is what we are looking for. And second half, if we continue and we see, now let's say that PC received a message, so I need to trigger the swap in. I materialize the object graph, and now it is correct. Okay, we do not have the problem of the duplicate C and D. So the thing is, how do I identify A and C? How do I know that the object that needs proxies are A and C? Because this is really difficult because in object-oriented system, objects do not have back pointers. So an object cannot know who is pointing to that object. So I cannot know if it is being referenced from outside the graph or not. And I cannot do a whole memory scan for every object of the graph because it's terribly slow. So the question is, how we efficiently can we detect these facade objects in order to proxify them? So Marea provides an efficient solution, and I will explain that as part of the swapping out and swapping in algorithm. Okay? So now I will explain the swapping out. This slide and the next one are the most important for Marea. It's an overview of the algorithm. So we have primary memory, secondary memory. We have this graph of the memory, and we have a global graph table that we will see why we use it. So let's say that we want to swap this graph. So the first step is to decide which graph we want to swap. So let's imagine we want to swap this graph, which the root is A. Okay. So first step is to assign a graph ID. So Marea assigns an automatically generated ID. Let's say in the case it's 42. Okay. Second step is to serialize the object graph. So we serialize this graph, and by default we use, in this example, we use the basic the object graph storage, which creates a file per graph that we swap and stores the file on the hard disk. So this is a simple file, which is the graph ID.swap, and this file will contain the serialized version of the graph. And it's important to notice that in this serialized version, each object of the graph has a position inside that chunk of bytes. So, for example, object A, it's at position 2, B, it's at the first position, and C at the third position. We'll see later why this is useful and needed during the swapping in. So, first step is to create an object proxy. So we we create proxies for every object of the graph. So we get PA, PB, and PC. And now I need to know to which object they will proxify. Okay? So what I do is PA and each of the proxies store information. They store two things. First, the graph ID. So you can see it's stored the number 42. And then each proxy stores the offset in the serialized stream of the object they proxify. Okay, A proxify, PA proxifies A, so it stores position 2, PC stores 3, and PB stores 1. Okay? And finally, we create a temporal table where we say, okay, A, you will need to be replaced later by PA and B for PB, etc. Now, the next step is to actually replace those original objects with proxies. Okay, so we will need to replace them. So what we are going to do here is we will update all references in the system that point to an object to instead point to its associated proxy. So for example, we start with A. So A, all the references to A will be switched to point to proxy. All the references to B will have the same effect. And then for C, so all references to C will be changed so that they point to the proxy. For this, we will see later in the implementation how we achieve this in our implementation. Now we finally stored some information in the graph table. We put at a key the graph ID, and in the value we put a weak array with all the proxies of the graph. And it's really important to know that it is a weak array. What is a weak array? It's an array that holds weak references to the object. And weak references, it means that if an object is only referenced by weak references, the garbage collector will collect that object anyway. Okay? So it is very important to remember that this is weak, as we will see later. Now, and this is the key point, when the GC runs, now we do not force the GC, Maria does not force the GC. When the GC runs, notice that there are no references from outside the graph to any of the original objects, not to B, not to B, and not to C. And there are not references from outside the graph to any of all the internal proxies. The only proxies that are referenced from outside the subgraph are the objects that proxify facade objects. Okay? So A and C. So now if the GC runs, 1E is the GC, of course. So it will only keep, the only options that will remain alive are PA and PC, which are the proxies for facade objects. And this is what we were looking for at the beginning. So the graph was completely swapped out, and yet just letting only two proxies in the image, in the system. And now this weak, because this was weak, so that's why this could be garbage collect. And now the size of this array is the size of the object of the graph. So there will be probably a lot of nils, because the only known nils will be the proxy for facade object. So we have a final compactation where we can compact in order to use less memory. Now let's take a look to the swap in. So this is the stage after the swapping out. So let's say that now a proxy intercepts a message. So it seems that the graph was needed later on. So the proxy will intercept the message and it will trigger the swap in. So for this I have implemented my own proxy library, as we will see later. But okay, let's say that PA receives a message and it needs to trigger the swap in. So the first step is to materialize the object graph. So taking this information, we can know which is the file that we need to search for. We materialize the object graph, so we get the materialized graph. And the serializer can also answer us an array with the materialized objects. And this is in the same order that it was previously during the serialization. Okay? So next step is to associate proxies with materialized objects. So it's the other way around that we did during the swapping out. So what we're going to do is, first let's take the proxy that that intercept the message, in the case PA. So first step is that we have several proxies for the graph. So we need to get the list of proxies that we will need to fix. So we get the graph ID, then we go to the graph table, okay, at graph 42, and we get the list of proxies. So this is the list of proxies that we need to fix for this graph. But then how do I know each proxy to whom it should replace later? I mean, how do I know that proxy A should later replace A? So what we do is we go object by object, proxy by proxy actually, and we get from the proxy the offset in the materialized object. So then we know that this proxy needs to replace the object at the position 2, when the case is A. And then we create a temporal table where we associate proxies with objects. And then we continue with the rest of the objects. So at the end, we know which proxy to whom we should replace them. Now it's time to replace them. So we replace as just as we did with the previous case. So we replace all pointers that were pointing to the proxy, now point to the materialized object instead. So now we can do some cleanings. Basically, I just need and remove all temporal data. So now if the garbage collector runs, it will just garbage collect this proxy because nobody is referring to them. So now we got back the original object graph that we have before the swapping. Okay? And finally, once we have finished, we need to forward the message that was intercepted by the proxy to the object that we have materialized, which in this case is PA. Okay? Step 0 and step 6 are from the toolbox, from the proxy toolbox, and 1 to 5 is from the object graph swapper. Now, I want to show you some problems that they may look easy, but they are not. For example, let's talk about the problem of graph intersection. This is how I call them. So let's say we have already swapped graph 42, the graph with A as a root. So now let's say that I want to swap this. Why not? This is an object graph. I want to swap it. It's unused. Okay, so if we follow the normal procedures, we assign a graph ID. So let's say in the case we assign 43, and we serialize the object graph. What will happen is that during the serialization, the serializer itself will send messages to the proxies, like give me your instance variable so that I can traverse the object graph, or give me your hash so that I can store you in a hashed collection, etc. So this, what will happen is that the serializer will trigger the swapping of this graph. So I will be swapping in the graph 42, which was unused, it was not needed. It is me that I need to swap another one. So of course, if we then continue with all the steps, this will work, okay. But this is not something that we want, and we would like to be able to swap the graph correctly without causing the swapping of another graph, because the first graph was still unused. So these are a lot of things that are not obvious. So if we continue, for example, with this, let's say that now we have a customized serializer that is able to serialize proxies without sending messages to them, so to avoid the swap in. So let's continue with a customized serializer that can deal with that. So now we continue the same steps. We create a proxy. So we have a proxy for a proxy, in this case a PPC. We have PD, and then we replace the original object with the proxies, just as we did in the other cases. Now we update the graph table. Okay, so it's 43, and these are the proxies. Now, pay attention now. If the GC runs now, nobody is pointing to the PC. It's only referenced from here, but this is weak. So what will happen now is that when the GC runs, we will lose object PC. And why this is a problem? Okay, let's continue. So now let's say that graph 42 is needed. So I swap it in. So okay, I swap graph 42, everything is okay so far. Now, when I try to swap graph 43, what happens? First, I have a nil here, because the object was garbage collect. This was used to point to PC, but it was garbage collect this, sorry. And in our serialized stream, when we serialize the object graph, the proxy was there. So when I try to now materialize the object graph and swap in, what I get is this. So I am getting a graph with a proxy of something that has already been swapped. And of course, this is not correct, and we need to solve it. And so regarding graph intersection, there are a lot of different cases, much more. So for example, there are a lot of scenarios to swap in the swapped out intersected graphs. So you can swap out one and swap in another one, swap out, then swap in. So there are a lot of possible combinations. For example, take the easy path, or I don't know, just avoiding creating a proxy for a proxy, like PPC. Okay, does not solve the problem either. So the solution is it's more complicated. I have solved all these scenarios in Marea, and I have prepared slides for the questions if you are interested to know who I solved it, but I don't have to explain it now, but if you want, I can answer you. Okay, now I will show you what I did to validate my project. So what we did is that we took the same applications we used previously at the beginning of the presentation, and we did the following experiment. We took these applications and we swapped out as much object graphs as we could. So we swapped out classes with all their instances. So we swapped them all. And then we start to navigate the application. We need to use the application to run the test, etc., so that to cause the trigger in of the needed graph. Okay? Then we also run the test. This is very useful to also know if Marea is correct or not. So the test should be exact. They should have the same result as if Marea wouldn't be running. And finally, we measure the differences in memory. So we measure how it was before using Marea and without Marea. Okay? So this is the result I got. So the x shows the project or the real apps that I test. The y-axis represents the percentage of memory. And now let's concentrate in just the first two bars, the blue and the green. So the blue is the original memory, so that's why it is represented by 100%. And the green, is the percentage of the memory after using Marea. So this is the experiment with using Marea after having swapped out everything, and when we have swapped in the graph that were needed. So as you can see, this is the difference that Marea could win in this case. So for example, for this case, it is around 45 to 40% of the memory. In this case, it is a little bit less. It's 25, and this one is different, and this is different. So it depends a little bit in the application on how much Marea is actually able to release. So the first conclusion is that in these cases, Marea was able to release between 25 and 40% of the memory, which I think for the moment it's already good. But still, now if we take a look to the orange bar, I call it measured minimum, and this corresponds, do you remember at the beginning of the presentation I present the experiment where I show you the percentage of used and unused objects. So this yellow bar represents the percentage of used objects, or the percentage of memory used by used objects. So what that means that there is still a difference, that we are still able to release even more to get to the real minimum usage. So why we cannot release, why the green cannot be as low as the yellow? Well, because it depends on the object graph that we choose as the swapping unit. So the second conclusion is that there is still a room for improvement, and with certain knowledge from the developer, from the application developer, we may be able to get even better results. And I will show you later that we have already started to work on this. So if we now measure the speed overhead, the idea is that we are able to deploy the application together with the database of the swapped out graphs. So that means that for a typical use case, the overhead will be 0 because the needed graphs were already swapped in. Okay? So most of the cases, since we have already swapped in during the first step of the experiment, during the execution of the application, most of the times the overhead is 0. But of course, there could be cases where there are graphs which were not swapped in during the analysis or the experiment part, so they may be needed to swap in later. So it's also interesting to measure these cases. So this graph represents the results we did in an experiment. So x is the graph size, so that means the amount of objects. And the y-axis represents the time for swapping in and for swapping out. So from this experiment, I got two conclusions. First one, that swapping in is faster than swapping out. And this is okay. I want that because for the swapping in, when you need to swap in is when the graph is needed at that exact point in time. So we should be able to swap in as fast as possible. And the swap out, okay, it's a little bit slower or less faster. And another conclusion is that because the serializer that we use is faster to materialize than to serialize. And the second is that the graph size has a small impact in the overall performance. There starts to be a difference around object graph of 5,000 objects. And if you can see, finally, the time it takes, so for example, a graph of 20,000 objects, it takes about 150 milliseconds, so it's not that much. And even though 60% of this is taken by the primitive that we use to exchange the reference between the two objects. I will explain that later. So the result could be even much better than this. So I will present a little bit about the related work. So at the beginning of my PhD, before starting to develop my proposal, I first analyzed which are the requirements that I want that an application level virtual memory for object-oriented system should satisfy. So I list these requirements, all of this, and then I decided to use these requirements as a comparison criteria to compare other related works. So we want an efficient object-based swapping unit. So we want a swapping unit which is based on objects, not in bases or any other similar structure. We want to be uniform. That means that we should be able to swap any kind of object graph, whether it is data or runtime entities or code or whatever. So we should be uniform. We should be able to reverse stuff. So that means that if you swap out, you should be able to swap in. So that's in contrast, for example, to remove, where you remove and you're done. We would like to have automatic swap in. That's what happens with all virtual memory. You do not need to trigger it manually. We want to have automatic swap out, even though we also want to have manually swapping out so that the user can say, okay, swap this. Then we want to be transparent, and these two items may be confusing. So on the one hand, we want to be transparent, but on the other hand, we want that the application developer can influence the swapping. And what I mean here is that the result of the application, when the application is running, it should get the same result whether it is swapping or not. It's like when you run an application and you don't know if the operation system is paging or not. So that's what I mean by transparency. And for controllability at the application level, what I mean is that the application developer should be able to take part of the decisions of what or when to swap. It should be able to influence. And finally, we would like to make it portable across all other languages or other operating systems. So we have analyzed different related works, and we have analyzed them or evaluated them with all these criteria. And there are different groups, so we try to group them. So the first group is the operation system related works. The most complicated part is that they are really difficult to be application dependent. So it's really difficult to customize or adapt it for a particular application. The maximum you could do is to create your own page replacement algorithm, but it's not enough most of the time, and it's still quite difficult to do it. It's not very easy for a developer. And finally, of course, it is not portable among other operating systems. So that's why I discarded them from the beginning. Then we have another way to reduce the memory used by application is to reduce the runtime while they run on. So for example, Java provides the Java runtime environment for mobile, for example, which is a stripped version. Okay, that uses less memory. Okay, but it is not reversible. So something that is not there, it's not there. It's not that you can swap in later if your particular need. Instead, so this is not the path that we want to go to reducing the runtime. And finally, there is a lot of different works at the language level or libraries. We have an orthogonal persistent and object database. We have large object-oriented memory. We have a tool which is to tolerate memory leaks, which swaps objects between parameter memory. And we have also evaluated image segment, which is an object graph swapper for Smalltalk. I cannot explain all of them right now, but as you can see, there's any that satisfies all the requirements that we want. And so this is why we did Marea. This is why I proposed Marea. This is the evaluation of Marea. So it satisfies all the requirements. Still, there is one in gray, which is the automatic swapping out. We are working on that. We have, for example, a VM which is able to trace object usage that we have customized the VM. So now we can ask which object has been unused for a while, and then we are trying to see how we can detect automatically graph of unused objects. But we are working on that. Now, some details about the implementation. So I implement Marea in Faro programming language. So my contribution is both Marea as a model and also its implementation. And besides, I have implemented from scratch all the subsystems of Marea, but only this one that I didn't. So object graph storage, so I reused the drivers that were already written for RAIAC and MongoDB, NoSQL databases. So that means that I can also store the graphs in a NoSQL database which could be remote or local. And then I have developed a proxy toolbox, a graph serializer, and the algorithm to swap out and swap in of Marea. So I will explain you just a little bit about them. So Fuel, it is a really fast serializer that we need to build from scratch because there was not any serializer out there which were able to serialize any type of object. And since in Marea we want to be uniform, we developed Fuel, which is able to serialize any type of object. It is general purpose, so Marea has customization on it, for example, to be able to deal with proxies. It has been really well accepted in the community. There is a lot of projects, both in industry and research, using it. If you want, I can show you, have a very cool demo and some links if you want to see some users. And it has been integrated in Faro 2.0. It can be ported to Squeak and even to proprietary Smalltalks like VisualWorks. And finally, it won the first place at the ISU Innovation Technology Award of 2011. And finally, we have a journal accepted about Fuel. So both Fuel and Ghost, as I will see now, it's a whole new project. So it has related works, it has validation, it has implementation model. I cannot, in the presentation, I am presenting Marea, but know that Fuel and Ghost are in itself a whole project in itself. So this is Ghost that we did from scratch, also because we wanted a proxy that is able to proxify all kinds of objects, like classes, methods, and things like that. And Ghost also provides low memory footprint proxies. This is very useful for Marea. It is able to intercept all messages, and this is a must if we want to be correct, because if the proxy is not able to intercept a message and answer itself, the application that is using that proxy, it will get a different result. So that will not be correct, so this is really important. And of course, also it is general purpose, and Marea has its own proxies, and it's very interesting. If you want, during the question, I can show you why Marea has its own special proxies, because it's interesting. And okay, we have also a journal accepted. Sorry, no, this one is not accepted. It was submitted, but we are doing now a measure revision. Okay, finally, I would like to tell a little bit about the implementation details about the become. So I told you to exchange all the references in the system from two objects, from a proxy and the original object. I use a primitive that the Smalltalk VM provides automatically. It's called become. But unfortunately, this is only available in Smalltalk. But I think it should not be difficult to implement in other languages, but we can discuss that later. And when there are different implementations of the become. So in Faro, which is the currently language where we have implemented Marea, it takes a full memory scan. So that's what I told you, that when we saw the graph, the 60% of the time for the swapping is taken just for this primitive. So, but of course, if you see, for example, other Smalltalk like VisualWorks or Shemstone, because of course they work, the become is really fast. It's just a primitive to change over a memory content or 2 pointers. So what I mean is that it is not that Marea needs a full memory traversal. It's a current limitation of Faro, and if we solve that, we could improve 60% the current times. Okay, so now finally the conclusion on future work. So the conclusion that I got from my PhD is that for a really improved automatic memory management, we need, apart from the GC, an application level virtual memory manager that should be based at the object level. And that's why I have proposed Marea, and I proposed its implementation, and I have validated. So that's the conclusion I got. Taking account into the results, I think it's correct. Marea, I mean, the graph, it's able to swap out and swap in correctly. So we are able to detect facade objects. We deal with all kinds of graph intersection. Both the serializer and the proxy toolbox are able to serialize or to proxify almost any kind of object. The proxies are able to intercept all messages. This is important for being correct. And finally, we have support for proxies. So for example, you may proxify some object, and then they are sent as parameter to primitives or things like that. So that's also difficult. So we have solved all of them. Regarding to maximize the memory we can release, so we have a really small proxies. So Ghost provides us low memory proxies, so we can have small proxies. And the fact of taking object graph as a swapping unit, one of the key things is that we only need a few objects, a few proxies to replace the whole graph. So we only need proxies for the facade objects. So that means that we can release a whole graph by just a few objects. To minimize the speed overhead, I have developed a fast serializer. We have, this is the most important one, it's the fast detection of facade objects. And finally, and this is related to what I told you of special proxies, that in Smalltalk, which is the language where we have implemented Marea, there may be some messages that swap in a lot of things because it sends messages, for example, to all the classes of the system or to all the methods, etc. So we have a special proxies that avoid possible unnecessary swapping ins. So that's also very interesting. Regarding future work, I plan to continue improving or to actually finish the automatic graph detection, but okay, the PhD 3 years, but I have already started, so I did the first step, which is to develop a visualization where in this case the large squares are packages and the small squares are classes, and the different colors indicates whether the class has instances that has been used for a while or not. So the idea of this visualization is that it helps the developer or even Marea to choose better graphs to swap out and therefore have even better results. So to do this, we first needed a customized VM, so I have modified the virtual machine of Faro to be able to trace object usage. So now I have a flag in the object header, and when an object receives a message, it is flagged, so I can query which object has been used for a while. So with this VM, we can continue with the automatic graph detection. And we have even better visualization. So for example, in this case, we can see not only if the class has been used or not, but also how much memory they represent. So in this case, with a simple view, the user can know which part of the system has been unused, and they represent more memory at the same time. So this is a tool to be able to swap better graphs. Then I plan to study a possible integration with the GC, because for example we may take advantage of the same traversal of the GC to flag or unflag things of Marea. Then we want to analyze partial swap in, so that means that when a graph is needed, instead of swapping in the whole graph, we swap in the graph, which is the transitive subgraph of the object that the proxy will then become. So we bring back only the subpart that is needed. But this has a lot of advantages, but disadvantages also, so we are still analyzing that. So this is my list of publications. I have 5 papers in conferences. One is about fuel. Another one is about, at the beginning of my PhD, that I did a deep analysis of image segment object swapper. So before doing Marea, I wanted to make sure what we had. Then we wrote a paper about the visualization that I have just shown you. Then we have a paper about efficient proxies in Smalltalk, where I present the implementation of Ghost. And finally, a paper which was with a theoretical background with all the problems and challenges when building a system like Marea. Then journal, I have four journals, 2 that were already accepted and published. So one is about the experiment that we did for image segment. The second one is about fuel, our serializer. And we did it with Martin. Martin was a master student working here in France for 3 or 4 months. So I supervised his master and we did fuel together. And then there is a paper about Ghost, a journal which was being submitted, but we are doing now a major revision. And finally, we sent a paper which is the kind of the end of the story, which presents Marea itself. We have submitted to CHOT, and we are still waiting for the response. So in summary, I have implemented a novel and efficient application-level virtual memory for object-oriented systems. There is no need for a specific VM, and everything is implemented in the language side. So the only thing that we need for the VM so far is only for knowing which object has been unused, but so far that is only for the visualization. We can still use the tool without that. So we allow users to influence or customize the virtual memory for its own needs. So that's all.